Hi everyone. First of all, I would like to thanks to the organizers for giving me the opportunity to contribute with a talk for this conference. My name is Rafael Bravo. I'm PhD candidate in physics from the Universidad de Chile. During my thesis, I've been working mostly on inflation. And in particular, this time, I will talk about the work concerning primordial non-Gaussianity that we did a couple of years ago. I'm currently further exploring. The work is based on two papers that were published almost 2 years ago, and another one that is work in progress. The first two works were made in collaboration with Sander Muig, which is currently postdoc at EPFL at Lausanne, Gonzalo Palma, who is my advisor, and Bastian Pradenas, who is currently PhD student at Johns Hopkins University. And the work is in progress is with my advisor, Gonzalo. So I'm pretty sure that most of you watching this talk are pretty aware of what is cosmology and what is inflation. But nevertheless, I always like to show these two pictures of the universe at two different times to emphasize the role of fluctuations. So in the two images here, we observe fluctuations on a homogeneous and isotropic backgrounds. In the case of LSS, we observe galaxies as matter fluctuations, and in the CMB, we observe temperature fluctuations. What cosmology does is to study the origin, the evolution, and the possible fate of the singularization experiment that we call the universe. And an important part of it is the study of the fluctuations. So concerning the origin, we know that inflation plays a crucial role. Firstly, was introduced to solve several puzzles of the hot Big Bang theory. But currently, we know that also provides the initial conditions for the structure formation. Also, it offers a quantum mechanical explanation of the fluctuations that we later observe as temperature or matter perturbations. Finally, it predicts two features that we observe nowadays in cosmological surveys: an early scale invariant power spectrum and the existence of adiabatic fluctuations. We know that all those features and properties can be provided by the introduction of a scalar field minimally coupled to gravity in the early stage of the universe. However, we don't know the final action for inflation because we don't really understand the microphysics behind it. So how can we build this action? In principle, we need some hints from two sides: theory and perturbation and observation. From the theory point of view, for instance, today there is a hot discussion on how Swampland conjectures can constrain model of inflations. Here is a little of advertisement of my work related to it. I'm not going to talk about this in this talk. But what is important here is that parameters shouldn't be in conflict with either theory or observations. In particular, in this talk, I want to discuss about this parameter, FNL. So the parameter FNL gives us account of the primordial non-Gaussianity, which is basically a measure of the self-interaction of the curvature perturbations. For instance, the naive prediction coming from single field slower inflation in what is called the squeeze limit is this one, which involves the spectral index of the power spectrum. This parameter, in principle, can be constrained through several observations. For instance, this is the current value coming from CMB temperature fluctuations released by Planck last year. By looking at the CMB, FNL can also be constrained through spectral distortions from large-scale structure surveys, can be constrained from the scale-dependent halo bias. Okay, I need to quickly introduce elemental ingredients to be able to explain my work. So basically, inflation, it's a period of the early universe where the moving Hubble radius decreases, which is equivalent to keep this parameter epsilon smaller than 1. As I said before, the energetic content capable of doing this is a scalar field minimally coupled to gravity with a slowly rolling potential. The field is separated in two contributions, an homogeneous background, phi naught, and perturbations around this background, delta phi. The equation of motion for the background part is the usual Klein-Gordon equation. And after using the slowly rolling condition, we can neglect the acceleration of the field, and we end up with an equation that has attractor solutions. Namely, the solutions are independent of the choice of the initial conditions. So it is useful to treat the perturbations in the ABM formalism and choosing a gauge in which we turn off the perturbation of the scalar field, and we move them to one of the scalar degrees of freedom of the metric tensor. This choice of the gauge is the so-called comoving gauge, and in this context, zeta is called the comoving curvature perturbations. After grading the action in this gauge in terms of the ABM variables and solving them, we can grade a perturbative action for the curvature perturbations. For instance, the second order actions is the following, which is proportional to the parameter epsilon. So perturbations are the key element in this story. So this is the behavior of perturbations inside and outside the horizon. The adiabaticity condition that I mentioned before, required to reproduce the power spectrum, demands that the perturbation freezes when they are outside the horizon, which means they have to remain constant until they re-enter the horizon. Conversely, the perturbations inside the horizon can oscillate freely in space and time. So how do we connect perturbations with observables in the sky? We do it through correlation functions. The 2-point function computing the second order action gives us the power spectrum, which is constrained through the scalar amplitude, AS, and the spectral index. Both numbers are well measured nowadays at some reference scale K0. And this is the current value of the spectral index released by Planck 2 years ago. Another important quantity in which this work is based is the 3-point function and the bispectrum, which tell us about the possible existence of non-Gaussianities. If we take one of the momenta of the perturbations going to 0 in the bispectrum, it is possible to define the local FNL parameter in this way. So what is the prediction from single field slower inflation for the bispectrum? That is not so straightforward to compute, since in this case we need to deal with non-linearities. In order to compute the bispectrum, it is necessary to find the cubic order action and extract the Hamiltonian from it. Then we put the Hamiltonian in the in equation, and the operator here, it's going to be zeta cube. Maldacena tells us that the bispectrum in the squeeze limit is related to the power spectrum through the spectral index in this way. This result is known as the non-Gaussian consistency relation. This result basically tells about how two short modes are modulated by a long one. And the power of this relation relies on that is a crucial test for all single-field attractor models of inflation. I want to emphasize that is for attractor. Okay, so there is another way to obtain this consistency relation based on two facts. One is the symmetries of the system. Another one is that the fact that the long mode modulate the short modes. So first we consider the ADM metric in the comoving gauge, and now I'm using the conformal type, but it doesn't matter. We know that the metric is invariant under the following transformation of field and coordinates. So here, zeta L is the constant long wavelength mode outside the horizon. Now we can split the curvature perturbations in their short and long contributions. And we identify the short mode in the original coordinate set with a full mode, which is solution of the same equation of motion that zeta, but with the spatial coordinate modulated by a long mode in this way. We are interested in computing the power spectrum for the short mode using this relation. And after expanding this relation in terms of zeta L and moving to Fourier space, we found the following. Now we can correlate this expression with a long mode, and what we found is the following. And we know that the squeeze limit appears in this particular way, and we end up with the bispectrum and the Maldacena's consistency relation. So we found it using symmetry arguments. So now I have all the ingredients and the recipe, and I can show you what we did. So I'm going to introduce a model of inflation which basically consists on a flat potential that was introduced by Kinney in 2005. During last years, people has been using this model as a mechanism to produce to generate primordial black holes. Something important here is that the curvature perturbation in this model satisfy the adiabaticity condition without freezing the superhorizon mode. Actually, the perturbations here exhibit a superhorizon growth. Also, the model is almost scale invariant. And an important difference with the slow roll is that in this model, the background solutions depends on the initial conditions. So it's a non-attractor background. This model in principle is not realistic because in this case, inflation never ends. But we can study it as a period previous to a slow roll. There are some people working on the transition of this model and the usual slow roll picture. So, but why the model is interesting from the point of view of non-Gaussianities? Because if we compute the bispectrum in this model a la Maldacena, what we found is the following. So this is an explicit violation of Maldacena's consistency relation. And why this happened? Can symmetries tell us something about this? Of course that symmetries can tell us something, and this is what we did. So same as before, let's consider the ADM metric in comoving gauge. And now we note that the metric and also the cubic order action are invariant under this transformation of coordinates and fields. And this time, the temporal coordinate is is also modified by, in this way. Here, T star is a reference time. For instance, it can be thought as the horizon crossing moment. Same as before, we can split the curvature perturbations in their short and long wavelength contributions, and we know that the short mode is related to the zeta prime mode, which is a full mode and solution of the same equation of motion, but now with the spatial and the temporal coordinates modulated by a long mode in this way. So here we know that if zeta L doesn't evolve, then it's going to be equal to the zeta L evaluated at horizon crossing moment, and we recover the standard attractor result. So same as before, we compute the 2-point function by expanding this term in terms of zeta L, and then we move to Fourier space, and we found the following. Now we can correlate this expression with a long mode, and we found the following. So again, if the super horizon mode freezes, this one, then this term is 0, and we recover the standard Maldacena's result. But if zeta L grows on super horizon scales fast enough for zeta L star to become subdominant, we found the following. And we identify this as the non-attractor part of the consistency relation. If we apply this result to ultra-slow roll, we note that the mode in this case scale as tau to the -3, and therefore the power spectrum scale as tau to the -6. So if we put the power spectrum in our consistency relation, we found the correct result. So this is our main result. A consistency relation that can recover the prediction of the bispectrum for modes that evolve outside the horizon. Again, this is our main result, but another interesting result is the following. So in the previous slides, we learned that long modes are indistinguishable from background. So it is possible to build a set of coordinates which takes that into account. In other words, an inertial observer cannot feel the influence of super horizon perturbations. That set of coordinates is called the conformal Fermi coordinates. And I don't have time to show how it is constructed. But at the end of the day, we found that at linear order, the coordinates looks like this. So here the quantities with the bar are the conformal Fermi coordinates. So it is possible to compute the bispectrum in this set of coordinates, and we found the following. We found this expression that can also be read in this way. So here is the bispectrum measured by an inertial observer, which is the contribution of the bispectrum computed in co-moving coordinates, plus a correction given by the chain of coordinates. So the bispectrum in the co-moving coordinates, we see before that is dictated by the symmetry of the metric. And what is interesting is that delta V is always exactly the inverse of this transformation. So as a result, we found that during inflation, after all modes excited the horizon, the observable bispectrum vanishes. This result was known for the case of slow roll inflation. And now we know that also applies for ultra slow roll inflation. So the genuine prediction of any attractor or non-attractor single field model of inflation is that the local observable FNL parameters should be 0. up to corrections that come from non-primordial phenomena, as for instance, propagation effects. So that was all. A brief summary. So we have generalized the well-known Gaussian consistency relation for non-attractor model of inflations by using symmetries. Also, we have shown that the observable squeeze bispectrum vanishes for single field inflations, the slow roll and ultra slow roll. And I think this is the most important point. If a sizable amount of local non-Gaussianity is detected, from where does it come from? Multi-field models, non-bunch Davis vacuum models, non-canonical kinetic terms. What other possibilities we can have? Thanks for your attention. Thanks.